Okay, so the YouTube site is on. So let me first start with a brief introduction about our today's speaker. So welcome everyone to join our CFSM seminar number 52. So today we are very happy to have Dr. Huashu Dou as the invited speaker. So Dr. Du is currently a chair professor at Zhejiang Science and Tech University since 2011. So Dr. Du received his PhD at Beijing University of Aeronautics and Robotics in 1991. Then he worked at Tsinghua University, the University of Sydney, and also the National University of Singapore from 1991 to 2011. His research focused on fluid instability and turbulence transition, and computational fluid dynamics, combustion, and detonations, and also the turbomachinery, non-Newtonian fluid, and multi-phase flows. So he has already published more than 160 papers and also 2 books published by Springer. So he's an AIAA Associate Fellow and also member of APS and ASME. So today, Dr. Du will introduce his recent work about the existence and the smoothness of solution of the Navier-Stokes equation. So Dr. Du, please start your presentation.
Thank you, Dr. Li, for the introduction. Ladies and gentlemen, I'm Huashu Dou. Today, I talk about the existence and the smoothness of the solution of the Navier-Stokes equation. This is the outline of the talk. Consists of 7 parts. This is the first part. Firstly, we discuss the advances in studies of Navier-Stokes equations. And this page shows the Navier equation for incompressible flow. This equation was established about 200 years ago by French scientist Navier and the English scientist Stokes. So this is the momentum equation for fluid flow, which derived from Newton's second law. Today, this equation is poorly understood by all of us. So, most importantly, the Navier equation describes turbulence. The turbulence is difficult to understand. So, in order to understand the Navier equation, we need both by the mathematics and also the physics. The Navier-Stokes equation is also the Clay-Millennium problem set up by 2000. Now, more than 20 years passed, but no one to solve it. The Navier equation, the solution, can be divided by the strong solution and the weak solution. The strong solution satisfies the PDE in every point in the domain. The weak solution satisfies the PDE in every value in points in the domain. The weak solution for 3D and S equation and the strong solution for 2D and S equation have been solved before. Now, the problem is the strong solution for the 3D answer equation. The French mathematician Navier in 1934 studied the Navier equation for initial data of finite kinetic energy. Navier has proven that there exists at least one global in-time finite energy weak solution for 3D. Navier also conjectured that the singularity of 3D turbulent flow is produced by the blow-up of answer equation. However, until today, his conjecture is not proved or disproved. Navier won the Wolf Prize in 1979. The Kolmogorov won the Wolf Prize in 1980. The Russian mathematician Lady Janskaya, a lady mathematician, she proved there is a strong solution of an answer equation for the 2D case. Now we study the 3D case. For the 3D answer, the strong solution, so in the past years, several mathematicians have tried to solve this equation by two approaches. The first approach started by Serene to study the weak solution. Later, Caffarelli and Professor Lian Fanghua also studied this equation and get the good result. The Caffarelli professor received the Wolf Prize and also the Abel Prize last month. The Constantine at Princeton University also think the singularity in the Navier equation is not related to turbulence if the singularity occurs for the Navier equation. Professor Feifman in Princeton comments, for solve the Navier equation lacks new idea and lacks the mathematical approaches. The Professor Gibbon at Imperial College suggested the spike may be the manifestation of true singularity, but no method to solve this problem. So this is very important about the spike. The Professor Tao at UCLA has approached this problem several years ago, but not successful. Recently, the Princeton mathematician Buckmaster and Waker proved the non-uniqueness of a weaker solution for 3D NF equation. And then the both received the prize from the Clay mathematical institution. For the DNS, the Cambridge University, Professor Moffat and Kimura did the DNS simulation for the vortex reconnection, and they find the vorticity in the flow field generated peaks. But they think the peak can be considered as a physical singularity, not a mathematical singularity. Dr. Yo and Professor Hossein at Texas Tech University also did the DNS simulation for the blow-up of the incompressible flow. They concluded the most of the blow-ups reported in the literature through the DNS have been found to be numerical architect or incorrect predictions. So I think the both conclusion is true. Why the NS has no smooth solution? Why? This is the singularity. If singularity exists, no smooth solution. If no singularity, the solution is smooth. The singularity 80 years ago and 90 years ago, the Professor Relay suggested the velocity varies with the time. If the velocity becomes very large, become infinite, this is called blow-up. Singularity occur. But several years past, nobody find the blow-up by the theory simulation. Experiment, no blow-up. So this singularity seems impossible. Later, I will show why it is impossible. Another singularity we called the velocity discontinuity. This is the velocity varies with the time. At some point, the velocity suddenly drops to zero. This is called discontinuity. This is the singularity of Navier-Stokes equation. Before, nobody knows this singularity. This is found by myself just 2 years ago. This singularity confirmed by the DNS, by the experiment, many experiments confirmed. This singularity is the cause of turbulence generation. Now, I have a summary for this section. Myself discovered another singularity, also the discontinuity, which is the cause of turbulence. Such singularity was previously unknown. Because we have discovered the existence of such singularity in turbulence, so NS equation does not have a smooth solution, regardless whether or not there is a blow-up. Now we go on the second part, advances in studies of turbulence. So turbulence is very important in the basic science and engineering. Already 140 years after the experiment carried out by Reno in Manchester. So many famous scientists have tried to turbulence. like Planter, Taylor, von Kamen, Karamagolov, 连家乔先生 John von Neumann, and Rayleigh, Rondo, Heisenberg, Feynman, Chandrasekhar, Ansak, all tried this problem, but no one is successful. This line, all the Nobel winner. The turbulence, there are two research areas in turbulence. This is very known. First one is how is the turbulence produced? Also meaning the flow, stability, and the turbulence transition. Second area, how is the fully developed turbulence sustained? How are the behaviors of fully developed turbulence? I have tried both the two areas in the past 30 years. What is turbulence? This picture, the top picture shows the laminar flow. The laminar flow is smooth. The streamline is regular. The bottom picture shows the turbulence. The turbulence is chaotic, random. So, what is it? In 1883, Professor Reynolds in Manchester did the famous experiment, showed the laminar flow transition to turbulent flow. This used the color dye, show the streamline. Laminar flow is smooth through the line. The middle pipe shows the transitional flow by the dye, and this by the spark visualization, so the transitional flow. The middle one at the top, the bottom one, the same one. So for the pipe flow, the Reynolds show the critical Reynolds number about 2000. In order to study the turbulence, many scientists proposed the theory called the theory of flow feasibility. All the theory proposed by a very famous scientist from Kelvin, Rayleigh, Aura Summerfield, Reno, Aura, Rondo, Lian Xixi, Stewart, Isaac, Herbert, Jefferson, all the feasibility theory. No one agrees with the experiment. No one. Me and the Carlos proposed the energy current theory. My theory agrees with all the available experiment. Now we have a summary. In the past years, the mechanism of turbulence generation is not known. Second, there is no criteria for turbulence transition in physics. Thirdly, turbulence has no theory. The only theory is the from Kolmogorov for the K41 theory. This theory is not from the first principle, but by the dimensional analysis, only a phenomenological theory is not reliable. In the past 100 years, people think turbulence is generated by increasing the reason number. This is wrong. Turbulence is not generated by increasing the reason number. Reason number is not a correct criteria for turbulence. If you understand this point, you will understand turbulence. When I talk about this point, everybody amazing. This is the channel flow, this is laminar flow, turbulent flow. The middle is the transitional flow. From laminar flow to turbulent flow, the transition flow shows the velocity profile distorted in this area. We should understand why distorted. This is the experimental data from the American professor Gator Hug. He showed the transition. This velocity varies with the time. You see, the velocity here will drop, generate the negative spike. This is the velocity discontinuity. Why discontinuity? This is correspond to the velocity profile visualized by the bubble, the hydrogen bubble. You see, if the velocity profile show inflection, here discontinuity. If no inflection, no discontinuity. This is the pipe flow experiment from Israel. Israel, the experiment. This is the pipe flow. You see the velocity profile show the inflection here. You see inflection. The inflection corresponds to the spike. You see this spike. The spike shows the inflection. No, if no spike, no inflection. The Kolmogorov in 1941 proposed this equation. This equation shows the energy spectrum versus the real number by this number. Yeah, this picture. You see, his scanning agrees well with the experiment for some experiment, but not all. So he proposed in turbulence, the vortex transfer the energy from large vortex to small vortex. So with this cascade, but he didn't know the energy in large vortex comes where come from. Our theory explained this. You see, this is a tornado. Tornado show a current example. Didn't depend on real number. The tornado moves about 60 to 100 kilometers per hour. You see, the curve of tornado is turbulence. You see, this turbulence, the curve. The outside of the curve, laminar, very, very clear. You see laminar. The linear number is thin. Linear number thin, very high. About yeah, very high. So the inside is turbulence, outside is laminar flow. Why? Same linear number. Why? So this is cannot be explained by the linear number. Another counter example for linear number. This is elastic turbulence experiment by the Israel scientist in 2000 published in Nature. The Reynolds number is very low, Reynolds number less than 1. The two rotating disks between the fluid generates the turbulence. Why? The Reynolds number is very low, less than 1, or generates the turbulence. So your Reynolds number cannot explain this phenomenon. So turbulence not depend on Reynolds number. Now, in the community, people think the Navier-Stokes equation can describe turbulence. Why turbulence is generated by the balance? The convective nonlinear term is high, much higher than the viscous term. So turbulence will occur. To balance the two magnitudes, this is wrong. The turbulence did not depend on the balance of the two terms, but depend on the interaction. The viscous term and the convective term interaction generates turbulence. Cannot be separated. This is first point. Second point, more than 100 years experiment and the simulations show Navier-Stokes equation can describe both laminar flow and the turbulent flow, I believe. But no current example showed that NS equation cannot describe the turbulence. Now, the third part, finding in turbulence by the energy gradient theory. In the past years, I proposed the energy gradient theory to study turbulence. This theory get a very good agreement with the experiment and the simulations. We already discussed the suitability of base flow and the finite disturbance, and also the relationship between the critical Reynolds number for the turbulent transition and the disturbance. According to the energy gradient theory, the Reynolds number is not the physics of the turbulence. The turbulent transition do not depend on Reynolds number, but on mechanical energy gradient. This is the channel flow, the laminar flow, turbulent flow. From laminar flow to the turbulent flow, so there is a mass transfer toward the y direction. In this direction, no force. No force. Why the fluid can move to the wall, to the both wall? Why? I guess the kinetic energy gradient. Because the kinetic energy gradient have a same dimension with the pressure. Yeah. Why I propose this theory? 20 years ago, more than 25 years ago, I worked at the University of Sydney, Australia. I studied the physical elastic flow. So this is a non-Newtonian flow. The flow passed a channel. This is a cylinder. This is the plate. So for the Newtonian flow, the pressure in this gap is a straight line. For non-Newtonian flow, the pressure very high near the cylinder to generate the pressure gradient. This causes the turbulence. Causes turbulence here. So I think this equation, because the Newtonian flow generates the turbulence depends on this kinetic energy. Non-Newtonian flow generates turbulence depends on pressure. So this mechanical energy, the gradient, causes turbulence. This is the proposed the hypothesis. This is correct or not, we will check. So then I propose this equation. This is the streamline. This is the normal streamline. This is the tangential streamline. So this is the total energy gradient. So this component causes the instability. This component causes the stability. Instability or not depends on the relative magnitude of the two components, meaning depends on alpha. Alpha 0, stable. Alpha 90 degree, unstable. Between 90 degree and 0 degree depend on lunar number and the disturbance. So the Navier equation. Navier equation for the pressure-driven flow, for like the channel flow, pipe flow. I write the K and the energy gradient function of this equation. This shows the alpha. The alpha equal to 90 degree. So the total energy is perpendicular to the streamline. This will generate turbulence. And this is alpha. Alpha is larger, more unstable. Alpha equal to 90 degree turbulence. Now we compare the theory with the experiment. This is the channel flow. The red line is my theory. You see, the instability occurs at this location. This is the pipe flow. You see, the red line is my theory. So instability occurs at this location. The turbulence is generated, started from here, from the red line position, about 0.6. And many experiments agreed with my theory. Here, I just show two pictures. Now, we discuss why the tornado, the outside lunar number is very high. Why no turbulence? We use the K to calculate. The energy gradient function is 0. 0 is very stable, keep laminar flow. This is the why the tornado outside is laminar flow. Why? K is 0. This is the relation about the energy gradient function with the disturbance. I derived exactly from first principle. So at the turbulent transition, the K is inversely proportional to the disturbance. If we write as the lunar number, so the disturbance is inversely proportional to real number here, because k is proportional to real number. This equation is correct or not, we compare with the experiment. This picture shows the pipe experiment carried out by the very famous Professor Hoff. Hoff published more than 10 papers in Nature and Science by experiment. He did this experiment for pipe flow in Manchester. So this is the transition data. This is turbulence. This is laminar flow. He published the paper in the PIL 2003. The last sentence he said, the experimental result is a straight line. Why we do not know. My equation explained this data. Exactly explained. Now the fourth part, existence and the smoothness of Navier equation with energy gradient theory. Now, we firstly establish axiom 5.3. So this is a track. A track, the dynamic equation can use this one. The work done by the engine is the FUT. F is the resistance, U is velocity, T is the time. If the work done by the engine, A is 0, the velocity is 0, meaning the truck will stop. So the equation we write with this one. If A is 0, velocity is 0. Very, very easy to understand. Now, in the fluid flow, here there is a fluid particle. Why is this fluid particle moving? Because the particle consume energy. If the energy is 0, the fluid particle will stop immediately. The particle like a truck. H now is the energy consumed by the particle. If H is 0, U is 0. Similar to the truck. So now we do the CFD. We have two approaches. First approach, use the continuous mechanics, use the Navier equation, use the CFD method, like the finite volume, finite element, finite difference. This is continuous method. Another is a discrete method, like SPH, DPD, RBM, is a particle method. The particle method, the principle is the particle driven by a force. Particle driven by a force. The force multiplied by distance is the energy. If energy is 0, the particle will stop. So now we get this axiom. If the total mechanical energy gradient along the streamline is 0, the velocity is 0. If partial E, partial X is 0, velocity is 0. This is accord is the axiom 5.3 in my book. So this no count example. I will use this axiom to rule the smoothness is existence of an equation. You see? This page, all the theory included in this page. Very simple. You see? This is Navier equation. In x direction along the streamline. This is Navier equation. The E now is the mechanical energy. In the flow field, if you do a DNS or do a RES, after you finish, you can plot the picture, plot the velocity field. You can find in your flow field, there are many points. The Laplace is 0. Laplace 0. There are such points. Laplace 0. If Laplace is 0, you see this equation. The right hand side is 0. The left should be also 0. The left 0. If left 0, the solution, this one, this is 0. This is 0. You know, the solution, no approximation. Exact. Laplace 0. The left is 0. Left 0. This is 2 term 0. Very exact. If part E part X is 0, U is 0. In the past 20 years, everything I have approved, only this step cannot go through. Partial E, partial X is 0, velocity 0. So I set up this axiom.
So can I ask a question here?
Hi.
Hey, Dr. Du, can I ask you a question here?
Hey, okay.
So I can understand that when you have the energy gradient is 0, the work is 0, so there's no acceleration. But I don't understand why the energy gradient equal to 0, the absolute value of U itself should be 0, because you can consider if there's if we keep the U is a constant. For example, you have the energy E is pressure plus the kinetic energy, it's rho v square. If I define the partial E, partial X equal to 0, what we can obtain is partial velocity X equal. I can understand that the gradient will be 0, but I don't understand why.
I understand what you said. I understand. This is with cost flow. Now with 2 equation, express flow. So, with cost flow, a particle consumed energy is the work done by the surround fluid. You see, if the part E part of X 0, the velocity is 0. If a fluid moving in uniform speed, this is inviscid flow, not viscous flow. You know, this equation is exactly from the ENS equation. So, just from the chart, if the particle consumes the energy is 0, the velocity should be 0. This is the key exponent. Yeah, this one. So, if this step is known by people, turbulence had been solved many years ago, because no one knows this step, so turbulence cannot be solved. Now, I set up this step, the turbulence is discovered. You see?
Okay, we can discuss later, but I currently I cannot understand this part. Let's move on.
Okay. you see, so this is the velocity. The velocity now is viewed by the disturbance. So you see, partial E, partial U, partial T is 0, meaning here or here. If partial U, partial T is 0, so the velocity is 0. So here, at this position, X is a wave. Just the next moment, generates the spike. So this is experimentally confirmed by the Kitty-Hall experiment in Sweden. You see, because the velocity profile changed periodically from inflection to normal, inflection to normal, inflection to normal, in space or with time. You see, if inflection, the Laplace is 0. Laplace is 0, meaning the singularity. You see, if the Laplace is 0, inflection, so generate a spike. Normal, no spike. So this is in a period one spike, in a period one spike. So this picture is predicated by my theory. You see my theory. Now we compare with the experiment. You see the experiment. This is experiment by Japanese professor Nishioka. You see the velocity. So this is spike, this spike, this is spike. This is the initial transition. Later, this change will become the disorder. So many other experiments for the boundary layer flow, same. So there is one discontinuity in a period at the instantaneously velocity distribution. The spike meaning the U0 across at a position partial E partial T0. This is the boundary experiment. You see the spike. My prediction velocity is 0. Actually not 0, about 60%, because the fluid is with cause. So the tip not 0, about 60%. Now I give a model for the turbulence generation. The Stanford professor Klein in 1960s did a very famous experiment, show the burst event in the transitional flow. Why burst occur? So this is my model. Show the velocity generate the spike at Laplace 0 generate the spike. If U negative, the P must the positive. P is the positive peak. Because U is compressive, the V and W, there is one at least is elongation. So U, the V and W, at least there is one positive peak. Maybe the both positive peak. This picture explained many experiments. Some professor did the experiment show the pressure generated the peak cannot explain where the pressure peak come from this one. This is the Kitty-Hall Professor Schletter. Schletter did the DIS and RES simulation for the channel flow. You see, at the initial transition, the velocity show a negative spike, one spike. The one spike in the downstream generate two spikes, three spikes, four spikes, then turbulent spot. This is why the turbulence is generated. Firstly, from the one spike, two spikes, three spikes, four spikes, then spot. The left picture shows the Kitty-Hall Professor Alf Redson and Johnson did the experiment. This is the U negative spike, the V positive spike. The turbulence stress, this is called the ejection and the sweep. This is ejection. Also called the burst. The Stanford experiment shows the burst. Burst is the ejection, the burst. The previous burst here. So why the burst generated? Before, no theory to explain. My theory exactly predicted this burst. Now I have a summary. The Laplace term being zero leads to velocity discontinuity, meaning the singularity, instantly in a period of disturbance. Because this singularity is not differentiable, so the solution does not exist. Because at the singularity, no solution, even if there are solutions in other areas. So there is no smooth solution in the global domain. So we get the theorem at the higher number, meaning the transition flow and the turbulence. There is no smooth solution to the Navier equation in the global domain. The singularity of the Navier equation is the cause of turbulence transition or turbulence generation, as well as the sustenance of fully developed turbulence. Now we have a summary. Okay. The nth equation, meaning a differential equation for incompressible fluid, is the conservation equation of mechanical energy in unit length distance. It implies the law of mechanical energy conservation. Thus, the energy consumed by the fluid particle or micro element is proportional to the velocity, because the energy loss cannot be infinite. So the blow up is not possible. So blow up not possible. For the incompressible flow, we only continuity equation, nth equation. This is the system of equations. The nth equation conserve the energy by itself. Now we go to the this section. In this section, I use the Poisson equation method to prove same conclusion as just section 4. Because the time this part we skipping. Now we go to the section 6, criteria of turbulence transition and turbulence generation. Now, according to my theory, the turbulence generation is by this singularity, this spike. In the simulation and the experiment, nobody find the blow up. Now, I have just explained. The blow up is not possible in incompressible flow Navier equation. So this is the only mechanism for turbulence transition, turbulence generation. Now we can conclude. It is still not known the blown up can occur or not for Navier equation in the community. However, regardless of blown up, S has no smooth solution at high real number due to singularity, because this is crossed by the discontinuity. There is evidence turbulence is produced by discontinuity. This is the 4 theorems obtained by myself. The necessary and sufficient condition for turbulence transition, turbulence generation, is that the energy gradient function is infinite, or this theorem, the necessary and sufficient condition for turbulence transition is the existence of a singular point of the Navier equation in the flow field. Now, we use the energy gradient theory to the Navier equation. We find the singularity. The singularity is the root of turbulence. In the community, many scientists study the turbulence with all these phenomena. The traveling wave was studied by the Professor Kurzweil in Cambridge University, and the Germany, the Eckhart, invariant solution. Dynamic system, feather, bifurcation, fractal structure, bursting, intermittency. What takes the cascade like the Kolmogorov, coherent structure, solidity, helicity, all the phenomena. All these phenomena, the root is singularity. Singularity are the origin of the turbulence related phenomena. If you understand my theory, understand the singularity, all these phenomena you can understand. So this is like the elephant, this is nose, this is body, this is leg, this is tail, like go on the conclusion. The energy gradient theory is a unified turbulence theory. It can describe flow, stability, turbulence transition, and turbulence. The necessary and sufficient condition for turbulence generation is that the singular point of Navier equation appears in the flow field. And now we'll go on the last one. Very, very important. There is no continuous smooth solution for ith equation for transitional flow and the turbulent flow. This is a Chinese translation for convenience of a Chinese student. What's new? The new is from ith singularity, the back burst turbulence. Ith singularity, not differentiable, no smooth solution. The secondly, for the turbulent transition, we should not balance the convective term and the viscous term. The mechanism is the interaction. Thirdly, turbulence is not caused by increasing by an increase of linear number by the singularity. The singularity is caused by the mechanical energy gradient. The discontinuity generates the singularity. This singularity is the mechanism of energy transfer from the mean flow to the fluctuation, meaning from a large vortex to a small vortex. It explains the K41 theory. The Chinese translation. What are wrong in the community? Just mentioned. Turbulence is not generated by increase of linear number. But by the interaction. Blow up is singularity. Discontinuity is the singularity. Turbulence is due to later, due to discontinuity, not a blow up. So my research contributed two very important to the community. Demonstrated turbulence is produced by the singularity of ith equation. Secondly, the regularity of ith equation has been solved, meaning there exists no continuous smooth solution in the global domain for transitional and turbulent flow due to singularity. So the double helix of DIA has unlocked the code of biology and opened the new area of biology. The singularity in turbulence is the core, is the molecule of turbulence. And this is a vortex. Generally, the singularity near the center of the vortex, near, not exactly in the center, near. So this is the singularity. So the turbulence is composed of many singularities, also many vortices, from large scale to small scale. Why the singularity located at the center of the vortex? Because here, the vortex center, the Laplace is 0. So, thank you very much.
Okay, so thank you very much, Dr. Du, for your very interesting talk about the singularity discovered in the turbulence theory. So if any audience have questions, you can unmute yourself and ask Dr. Du directly.
Hi, Jen. Maybe I can start by asking
Sure.
the first question.
Sure.
So hi, Dr. Du. Thank you very much for the very interesting talk and also sharing the very powerful and unified energy gradient theory. So that is very, very interesting to me. So my question, in fact, so first, let me confirm my understanding. So seems according to the EGT, we can identify when and where the turbulence can happen within the flow field. Is that correct?
Yeah. According to the energy gradient theory, the turbulence can be started, can be generated at a location. This location is the energy granted the angle the alpha equal to 90.
Mm-hmm.
Where the alpha is the largest, where the alpha near 90 degree, where the turbulence is generated.
Yes, and also seems the energy gradient theory doesn't influence the formulation of Navier-Stokes equation at all, right? It's just some kind of criteria to help us determine when the turbulence can happen, right?
Yeah.
Okay.
You can determine by the Navier equation. For example, if you do a DNS or do a LES for a turbulence flow, after your simulation is finished, you can carry out post process. In the post process, you use the UVWP. You can calculate the K. If the K is very large, for example, about 10,000. So this is the singularity. Here generates the turbulence.
Okay, yeah, then my question is, so if the energy gradient theory doesn't change any term for the Navier-Stokes equation, then say when we can know the turbulence happen somewhere inside of the domain, then basically it won't influence the flow field, like the velocity field at all. Then I'm just wondering, so if we still use the Navier-Stokes equation to solve the whole like a fluid domain, then what we should modify to handle the turbulence phenomenon?
How to deal with this matter? So if you want to control turbulence, for example, you design airfoil or design a turbine. After you finish the simulation, you can carry out the post process. You find where the singularity is very large. The K is very large. You can redesign this area. After you redesign this area, you do the simulation again. If you find the K, the value is reduced, so the instability is improved. So the turbulence transition is delayed, or the turbulence level is reduced.
I see. Okay, got it. So basically, say because I'm not in the field of turbulence, so to me, so seems I can just solve the Navier-Stokes equation without any prior like knowledge regarding the turbulence, and then maybe I can ask like an expert like you to identify the turbulence like area, and then we can redesign, say, the velocity field or the structure to prevent the happening of the turbulence phenomenon, right?
Yeah, you can.
Okay.
You can.
Yeah.
Just take an example of the tornado. The tornado in the core is turbulence. Outside is the laminar flow. This is because the outside is free vortex. Free vortex is very stable. The energy gradient function K very low, is 0. So we have used this theory to the draft tube of the hydro turbine and also the cyclone separator. If we increase the free vortex, the flow is more stable.
Okay, thank you very much for the further explanation. Really appreciate that.
You're welcome.
So any other question from our audience? Yeah, if not, maybe I can ask my questions. So I have two questions about the theory. And the first one is you mentioned when you have the partial U, partial T equal to 0, at that instance, the partial E, partial X were equal to 0. The energy gradient will be 0, so that you will have the velocity goes to 0. But based on the experiment measurement, or you will see the spike data, usually the velocity only reduced to 0.4 or 0.5. It's not goes to 0. I'm not sure why, or that you already show many different experiment data. I just see the measurement about the velocity just drop half of the maximum velocity. But your theory said the UA should goes to 0. I'm not sure what's the reason to generate this 50% difference.
Thank you for your question. Because the singularity has no volume, has no length. The singularity just one point. The volume is 0. So theoretically, the velocity is 0 because the fluid is with the course of fluid. So the velocity becomes 0, cannot be dropped to 0, just drop to 0.6 maybe. Like we have a birthday cake. A birthday cake we place on the table. If a sand drop from the roof, the cake will be hit a hole. A particular sand cannot be dropped to the bottom. You know, just to the middle of the cake, like theoretically can drop to the 0.
So can you predict the difference, or you cannot use the theory to predict why it's dropped to 0.4, 0.5, then stopped?
By the theory cannot.
Okay.
By the theory, we just can theoretically just show the theoretically become to 0. But by the DNS, LES, or experiment, just the 0.4. like the 对吧 the spike 叫 spike yeah.
Yeah. Okay. Another question is about the definition of your energy gradient. So you define the energy gradient along two directions. One is the streamline direction. Another is the perpendicular direction. But actually, in all the, for example, even in the channel flow, if you consider the perpendicular direction, actually you have two directions. You have the V direction and the W direction, and both direction is partial n. And we know the V direction and the W direction is definitely different. I'm not sure in the theory how you identify the difference between the V direction and the W direction in the theory.
Thank you, Dr. Lee. This is a good question. So, because through the streamline, the S direction, no problem, is tangential to the streamline.
Yes.
N direction is in this plane, the Y direction and the Z direction, the two vectors, the resultant vector is the partial E part N, you know. This partial E partial N is composite by two directions in Y and Z, you know. The root of the square of Y and the Z direction is this one.
Yeah, but based on the because of, for example, at the singularity, when the U drop to 0 and you have, because you have to keep the energy consistent, so you have the V and the W will increase positive, right? So you mentioned that at the later slide, so when U goes to drop, the V and the W will increase.
Yes,
yeah,
positive.
The magnitude is different. I'm not sure, because in your theory, you cannot tell the difference between V and W. So when you consider U goes to 0, V and W will increase. How V and W will increase? They are the same or they are different?
This is depend on water flow, because the flow is three-dimensional. For example, in the pipe flow, is three-dimensional. In the Z and the Y direction, the velocity is distorted. The V is the V and the W may not be equal.
Yeah, but in theory, you cannot tell the difference, right?
I cannot tell.
But how can you later determine how much V increase, how much W increase in the?
This can determine, because the total mechanical energy cannot change.
Yes.
The U, V, W, the kinetic energy, plus the P, the total mechanical energy is constant.
Yeah, this is three variable. You only have one conservation equation, right? You have only have energy conservation. You have three variable. You cannot determine how the V and W, how the energy distributed along the Y direction and the Z direction, right?
Yeah, cannot be determined in detail how much in each component, but the principle is true. This is planned how the energy transferred from the mean flow to the turbulence. Yeah, in the Kolmogorov, the K41 cannot explain this process. For me, this is firstly explained this phenomenon. Yeah.
Okay, thank you. So any other question from our audience? Okay, if not, then we will end our seminar today. So if you have additional question, you can contact Dr. Hua Shudu directly. Okay. Then thank you all for attending today's seminar. Thanks, Dr. Du, for your wonderful presentation.
Thanks, Dr. Li, and thanks, Joanne.
Thank you, Dr. Do.
Thank you.